Hello everyone. In this particular video, we are going to be looking into the third unit of IoT sensors and devices. And the third unit is about digital pins as input and outputs, how to read analog quantities, PWM pins available. All these are the pins available in the Arduino. Then we are going to look into the communication through serial ports. So you'll first have to know what is a serial port and how to communicate using them, the transmitting and the receiving part, and one bit format, and that is what you're going to see there. Next, we are going to look into how you will be interfacing your DC motor and the relay to your particular Arduino. So the basic programming part of your Arduino is going to be starting in the third unit from here. Okay, so we look into our third unit in detail now. So first we'll be looking into the digital pins as input and output. So as you may remember, we have totally 14 digital pins and they can either be used as input and output. So now we'll be looking into its applications in detail. So this is the basic pin diagram of an Arduino. And as you may remember, this blue color line representation over here, this blue color digital represents the particular digital pins available in your Arduino. And the green ones over here represent the analog pins available over here. So you can see that there are 6 analog pins A0 to A5 and you have digital pins 0 to 13. So 14 digital pins are over there available. And these two are not usable by the user. Next one we have all the black color marked pins over here, which is for the power and ground. So power, reset, ground, all these combined together. All of these are for the power signals. So these are the most common ones that we'll be using over here. And the ones with the red tick mark over here, you can see that 6 of them are available. And these are the ones which will be used in PWM, which we'll be looking into detail in our particular upcoming slides. And we have the TX and RX pin that is more specifically used for serial communication that you can see over here. So our second topic in the second lesson is all about this TX and RX over here. So I hope you've got an outline about this pin diagram. Take 1 minute and look into this pin diagram, then probably continue into this video later. Okay, so we will now move on into the particular topic. So digital pins. The pins on the Arduino can be configured as either input or it can be configured as output. That is the advantage of this digital pins. Arduino and Mega pins default to pin inputs. Default it is as input. If you do not program it your Arduino and you do not specify input or output, by default it will take it as an input pin. And they don't need to be explicitly declared as input with pin mode. So pin mode is the keyword that you'll be using to determine whether whether your digital pin is input or output. So if you do not explicitly require this particular explanation of them when you are using them as inputs, pins configured this way are said to have an high impedance state. So by default, it is in an high impedance state over here when it is because it is declared as an input. Input pins make extremely small demands on the circuit that they are sampling equivalent to the series resistor of 100 megaohm in front of the pin. So it has a 100 megaohm in front of the pin connected to the particular supply. That is why it is in the high impedance state and considered as a default input pin over there. This means that it takes a very little current to move the input pin from one state to another and can make the pins useful for such tasks as implementing capacitive touch sensor, reading a LEDR photodiode and so on. So this 100 megaohm means a very less current is going to be flowing through the pin, which means that your device, input devices that are connected to the input pins over here, they can be very sensitive. They are very sensitive devices to current can be interfaced to them. That is the advantage of that. And the devices that are very sensitive to current, as you may be aware, is the capacitive touch sensor because it depends upon the signal that you make contact with. Please go to the unit 1 and look into the touch sensor which we've seen earlier. You'll be able to recall that. And also about the reading of an LED as a photodiode. Both of these are basic examples of the applications of this requirement of the 100 megaohm at the input pin. This also means, however, that pins configured as pin input mode with nothing connected to them or wires connected to them that are not connected to the circuit will report seemingly random changes. Okay, so that is the main problem here. They will have random changes in their input value in a pin state, picking up electrical noise from the environment or capacitively coupling the state of nearby pin. So when two conductors are placed near each other, what will happen is in between you have the PCB material which is going to be an insulator. On either side, if you have two pins which are going to be conductors, two conductors separated by a dielectric is by default a capacitor. So this capacitively coupling effect is going to take place over there unless and until you have the resistors over there to suppress the flow of current or make sure that both the particular pins are on the same having the same voltage. That is a concept over here. Often it is useful to steer an input pin to a known state if no input is present. So if no input is available over there, the idea is to steer it to and not to an unknown state, which is a problem that we saw on this point, but to steer it to a known state. This can be done by adding a pull-up resistor to 5 volt or a pull-down resistor to ground on the input. So either you can use a pull-up resistor to the power supply or you can have a particular pull-down resistor to the particular ground over there. So I hope you can understand that with the high input impedance in my particular Arduino board, I can either connect a pull-up resistor or I can connect a pull-down resistor. And the best value that we normally use for the pull-up and pull-down is a normal 10k ohm resistor for this particular purposes. There are 20 kilo pull-up resistors built on the Atmega chip that can be accessed by software. So 20 kilo ohm pull-up resistors are the ones that can be accessed by our particular Arduino IDE softwares. So we can utilize them. These built-in pull-up resistors are accessed by setting the pin mode, and you have to give this particular keyword. When application requires, you need a high pull-up resistor because this is available on the Arduino. And by default, as I told you, 10 kilo ohm is the one implemented. If you want to use the 20 kilo ohm, you will have to program it using the keyword input pull up. So, this effectively inverts the behavior of the input mode when high means the sensor is off and low means the sensor is on. So what is going to happen over here is it is going to toggle the inputs away that are coming. So when a high input is coming, it means the sensor is equivalent to off state, and low coming means the sensor is particularly in on state. The value of this pull-up depends on the microcontroller used. So this value of the 20 kilo ohm that we are talking about over here, it depends upon the microcontroller used, whereas the standard value that we normally use is 20 kilo ohm. But they are guaranteed to vary between the range of 20 kilo ohm to 50 kilo ohm depending on the microcontroller board available. On the Arduino Do, it is between 50 kilo ohm to 150 kilo ohm. Due, the particular microcontroller type that we saw in the second unit, has a particular pull-up resistor of 50 kilo ohm to 150 kilo ohm. So, depending upon the value available, you can program them accordingly and use them accordingly. So, when connecting a sensor to a pin configured with input pull-up, the other end should be connected to ground. So, you know that there should be a power supply there. When the particular pin is not in use, the remaining unnecessary current should be flowed to ground. So, the other end should be connected to ground over there. So, to make it a particular closed loop. In the case of a simple switch, this causes the pin to read high when the switch is open and low when the switch is pressed. Okay, so we saw that the toggling state was happening in the case of sensors. When it comes to a switch, the same concept is going to happen. When it will read high when the switch is open. Normally, when it is open, we will say that it is low over there, which means no current is going to flow. But due to the toggling effect, when the switch is open or not pressed, it is equivalent to high, and when the switch is pressed, it is equivalent to low, toggling effect taking place. So the pull-up resistor provide enough current to dimly light an LED connected to a pin that has been configured as input. Okay, so it is bright enough. The resistor value, pull-up resistor value, is good enough to let enough current flow to the LED and make it glow. That is the advantage of it. If LEDs in a project seem to be working, but very dimly, this is likely what is going on. Okay, so when you are using this LED in your particular project on the Arduino board, and you may think that why is the LED glowing so dull? Reason for that is the pull-up resistor value. Depending upon that value, the brightness of the LED will change. Pull-up resistors are controlled by the same registers in chip memory locations that are available in your board that control whether a pin is high or low. So the same registers in your Arduino board that is used for controlling that is the one that is used for controlling whether it is high or particularly low. So next, we have the particular pin configuration to have pull-up resistors turned on when it is pin is an input. We'll have the pin configured as high if the pin is when it is there, and when switch to an output with the pin mode. So you can make it as an output pin also using this particular same concept of pin mode. This works in the other direction as well, and an output pin that is left in high state will have a pull-up resistor set if switched to an input pin mode. Okay, so the vice versa takes place over here. Digital pin 13 is harder to use as a digital input than the other digital pins because it has an LED and a resistor attached to it that's soldered to the board on most boards. So when you look into the Arduino board, in the first slide that we saw, near pin number 13 there would be an LED and a built-in resistor. So if you want to run the first default program of an Arduino, you will come across blinking LED, and that in that you will have the inbuilt pin that is being used by default, and that inbuilt pin is nothing but the pin number 13. So why is it called the inbuilt pin? Because in that particular inbuilt you have the LED on the inside. You do not require an additional LED to run your particular program. So to run that LED, you know that you require a resistor. So it is quite difficult to use pin 13 compared to configuring other pins on the Arduino. Okay, so that is the concept that they come to say. If you enable its internal 20 kilo ohm pull-up resistor, it will hang at around 1.7 volt. Okay, already there is a resistor available on pin 13 for the LED, inbuilt LED, and if you are going to enable the 20 kilo ohm pull-up resistor, total what is going to happen is the resistance increases over here. Other pins do not have that particular additional resistor, but this pin number 13 has that particular additional pull-up resistor. So what will happen is the current is going to get even lower, so and the voltage is going to get dropped across both the resistors. Okay, so when the you know that when two resistors are connected in series, the voltage drops across each of them. It is not going to be the same. So what will happen? It will become 1.7 volt instead of the expected 5 volt that is to be coming across, because 20 kilo ohm will be only able to get the 1.7 volt available. Other pins you will be getting approximately the full value, but due to the additional resistor in pin number 13, this is a drawback happening over there. So which means your output will be getting only 1.7 volt, which is not an expected output for running any output devices, because the onboard LED and the series pull-up resistor pull the voltage level down, meaning it is always return low. 1.7 will be considered as a low value only. So the reason for that pull down is you see that the LED resistor in series is connected again in the series with the 20 kilo ohm. So there is going to be drop across three of them, and the drop across the 20 kilo ohm is going to be so low, 1.7, that it is considered to be a low value here. If you must use pin 13 as digital input, set its pin input to input and use an external pull down resistor. So it is preferable that you use a lower resistor value at the and connect it externally using this particular. If you want to use the pull down resistor concept over there. Okay, so that is what you need to do if you are using pin number 13. Pins configured as output with pin mode are said to be having in a low impedance state. So I told you earlier, input is of high impedance, whereas the output is low impedance normally. Any pin that you see. This means that they can provide substantial amount of current. Low impedance means low resistance. Low resistance means the output can get the maximum of the current. That is the advantage over there. Atmega pins can source a sink up to 40 milliamps of current to the other devices. So that is the advantage of using a low impedance state over here, and the Atmega can do that. This is enough current to brightly light up an LED. So more the current, the LED is going to be bright enough, or run many sensors, for example, but not enough current to run relays. That is not sufficient enough for relays. So that you will have to look for an alternate solution. We'll continue in the next video.